Welcome back to the second part of our journey through the fascinating world of waves. In this video, we will dive deeper into the fundamental concepts that underpin the physics of waves. From the rhythmic dance of ocean waves to the ground-shaking force of earthquakes, this video will unlock the mysteries behind these phenomena, all through the lens of physics. Today we will explore the intriguing relationships between wavelength, frequency and other areas. Understanding them opens doors to a realm of knowledge that is both breathtaking and profound. We will use equations and visual aids to demystify complex topics, making them accessible for everyone. So whether you are a seasoned physicist or someone simply curious about the world around you, this video is for you. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to lesson 2, where we are learning the physics behind the fundamental properties of waves. Before we go ahead in lesson 2 of today's video, here is a quick recap for those who have missed the earlier video. So in the first video, we started learning why we should study waves, because these are the foundational cornerstones of classical physics, quantization of energy, quantum mechanics and other phenomena. We also learned what is the importance of wave mechanics in daily life, because it not only helps from electronics and medicines, but it goes deep into material science, quantum computing, lasers, how MRI scanners function, the ultrasound machines function, and how the transistors and the entire computing and electronics world has been revolutionized with the study of waves. We also learned what exactly is a wave, how far is one crest to the next. We also have looked deep into how often do crests come, the concepts of frequency as well as the concept of displacement. We have also looked earlier into what is called an amplitude and what is the frequency and angular frequency and many other things. So those who have missed my earlier video, lesson 1, you can look into the I button. I have given all the things in details. So these are the concept. Apart from that, there were various questions which I have answered in lesson 1. Now in this video, first we need to, so this is actually the video wave fundamentals. It is there in my playlist in Physics for Students, which you can watch. Now first, today we will watch and look into some of the basic wave relationships which are very important in our understanding of wave mechanics. Now the first is that many of the basic wave parameters, I would say, defined that we have done in the previous section are related to one another in a very simple algebraic equation. For example, this one where we are talking about frequency, that is f, and how it is related to the period, which is denoted by t, is simply by this equation. So what does this equation tells? That the equation tells you that the frequency and period are inversely proportional to each other. This means that longer period corresponds to lower frequency and shorter period corresponds to higher frequency. And we have also found that units of frequency are basically in cycles per second. And the units of period are just the inverse, so would be seconds per cycle. So as you can see in the earlier video, we have actually understood what is a period by a general, I would say, graphical representation. But this is much more important because we are putting into mathematical equations to make things easy. So the unit of frequency or cycle per seconds, which is expressed as 1/s, or minutes per second or something like that, and the units of period are just the inverse, as you can see, seconds per cycle. So this is what important. Cycles per seconds equal to 1 by seconds per cycle. Now apart from this unit of cycles, etc., another important and the most powerful, I would say, equation that relates is the wavelength, frequency and the frequency of a wave, which is this one, lambda f, which is equal to 0. Let us look a little bit closer into this equation, because this is going to occur repeatedly in our wave mechanics. So if we take this equation, lambda f equals to 0, we say lambda is the wavelength, f is the frequency and v is the speed. So now the thing is that what happens typically in this case, that we know that speed is equal to distance by time, which comes as of here. So if you put v, then the distance would be the wavelength, the length that is from one part to other. I've explained this in my earlier video, and time is obviously t. And since we know that t equals to 1 upon f, so what we do is that we just replace it, and then it becomes v equals to lambda 1 upon f, and then it becomes v equal to lambda upon f. So this lambda f upon v, in either way we can write it, is actually considered the units of wavelength multiplied by the units of frequency. So what we can do is, from here we can take it further, and we can write this can be written as meters per cycle multiplied by cycles by second equal to meters by second. So what it is, that this part, that meters by cycle, is basically the unit of wavelength. Cycles by second per second is the meter of frequency, and meters by second is the frequency of velocity. So what we have done is that we have written all those things in terms of lambda f and v, and I have shown you very simple how this lambda f upon v actually comes into. Okay, so if I take this equation, and what we can see is that it shows that what this equation tells, that it allows you to find the speed of a wave if you know the wave's wavelength and frequency. So for the waves with same speed, this lambda f upon lambda f equals to v. Now the thing is that as you study waves, you are likely to encounter many situations in which you are dealing with waves of the same type that are moving at the same speed, such as electromagnetic waves. We will see that. So here, as you can see, that lambda actually means that if the wavelength is long enough, frequency is, as I told you, the frequency must be low, and to make it constant, we make it as v. This is actually what this equation tells, and this is for waves with the same speed. Now you see that when we are moving at the same speed, such as electromagnetic waves in a vacuum, which actually travels at the speed of light, in such cases the waves may have a different wavelength lambda and a frequency f, and the product of the wavelength and the frequency is equal to the wave speed. This means that as long as the wave speed v is constant, waves with longer wavelength, that is large lambda, must have lower frequency. Likewise for waves with the same speed, if the wavelength is short, small lambda, the frequency must be very high, that is the f. So as you can see here, this is actually the electromagnetic waves. So this is the wave of the same type that are moving in the speed. Now you see, for this kind of electromagnetic waves, as I told you, the waves may have different wavelength lambda and frequency, but the product of the wavelength and the frequency must be equal to speed. So this lambda f upon equal to v, actually what it tells is this one. This means that as long as the wave speed, that is v, is constant, this is important. Waves with longer wavelength, that is with a large lambda, must have a lower frequency, small f. Likewise for waves with same speed, if the wavelength is short, that means small lambda, the frequency must be large. So actually this is the concept which is written in terms of the equation, which I was just telling you. Now what happens is that for sound waves, which actually have a we can tell a constant speed under certain circumstances, the frequency corresponds to the pitch. So here is a schematic diagram, a kind of a more or less overall diagram to make you understand about what is a high pitch sound and a low pitch sound. So what happens in this case is that frequencies corresponds to pitch in case of a sound wave. So low pitch sound you can take, such as the bass notes of a violin or a rumble of a passing truck, etc., must have long wavelength. And high pitch sound, such as for example a flute or a piccolo that you are playing, must have a short wavelength. This is how it happens. Now typically for electromagnetic waves in the visible portion of the spectrum, as you can see, I have taken this from this website. So typically for the visible portion of the spectrum, frequency corresponds to the color. Just as for sound waves, frequency corresponds to the pitch, for electromagnetic waves, frequency corresponds to the color. So the relationship is between the wavelength and frequency means that low frequency, for example this one, you can see this is a higher frequency which has got a kind of a bluish light, I can say, and a lower frequency which has got a kind of a reddish light. So as just in case of a sound wave, frequency corresponds to the pitch, in this case for electromagnetic waves it actually shows the spectrum. So those which has got a higher energy, I would say shorter wavelength, it will be a little bit bluish in color, and that is why we see the colors of the stars also according to the hydrogen spectrum. And for those who have got a, I would say low frequency, the red light has for the lower frequency it has got the red light, and for the high frequency it will be the blue. So accordingly it happens. Now as far as right now the video is concerned, we have learned between the basic relationships between the wave and the frequency, how do they look, the high pitch and sound pitch. But apart from that, you must be wondering that do these wave mechanics at all helps us to predict something or become something which is very useful to practical lives? This is something which will be coming up in the next part of the video. We are going to learn something very interesting and something very important. Those are called P waves and S waves, coming up in the next part of the video. So around 4 a.m. Local time on Monday, February 6, 2023, two tectonic plates slipped past each other just 12 miles below southern Turkey and northern Syria, causing a 7.8 magnitudes earthquake. Right on the screen what you can see is the aftermath of the earthquake in Syria. So it was the largest earthquake to hit Turkey in over 80 years. Then just 9 hours later, a second quake registered at 7.5 magnitude struck the same region. So this, both the striking, one in the Turkey and one in Syria, we can call the double effect of intense shaking collapsed thousands of buildings and killed over 20,000 people, leaving behind a humanitarian crisis in an already vulnerable area. The epicenter of the quake was near the city of Gaziantep, where there are currently hundreds of thousands of Syrian refugees. Aleppo, a city in Syria which has already been destroyed by civil war, also felt the brunt of the quakes. Now the question is that, can we predict earthquakes? How do we measure earthquakes? That is the kind of a danger which has happened, and somehow the seismic measurement was unable to predict, or there was a problem. So let us find out that how we can predict, or I would say how do we measure the earthquakes. Now there are two concepts. First one is called the P waves. Now P waves, that means the primary waves, actually are the first seismic waves which are registered in the, I would say, seismograph. So these are actually longitudinal waves. We will soon see what is a longitudinal wave, which means that the particles which are traveling through the medium vibrate in the same direction as the wave propagation. So you can see, you can make it at home by a spring or so. This is called longitudinal wave. So another feature is that this type of P waves travel through solid, liquid and gases, and their speed depends on the material that they are passing. So all solids, in solids they travel the fastest, followed by liquids and then by gases. So they are actually the fastest seismic waves that travels at a speed of 13 kilometers per second. And if I consider isotropic homogeneous solids and I consider P waves which are traveling in a straight line, the particles in the solid will vibrate along the axis of propagation, that is in the direction of motion of the wave energy, and the velocity P waves in that medium is given by this equation. So let us remember one important thing is that P waves are basically the first seismic waves. They are called the primary waves. They are longitudinal waves. They travel through solid, liquid, gases, and they pass in solid as the fastest. And if I take a isotropic medium where the P wave is traveling along longitudinally, that is the particles in the solid vibrate in the x-axis direction. Now this is the equation which it happens. Similarly, there is something which is called S waves or a secondary waves, which arrives a little bit late in a seismograph. These waves are basically transverse waves. We will also see what is a transverse wave. So this is a kind of a transverse wave, which means the particles in the medium vibrate perpendicular to this one is vibrating along the x-axis, just opposite will vibrate perpendicular to the wave propagation. So S waves actually can travel through solid materials, not through liquids or gases, and their speed is much lower than the P waves. And S waves are generated by earthquake, but it arrives late in the seismograph. They are also known as secondary waves because obviously they are slower than the primary waves. The S waves are shear waves. That means that they have got a side-to-side motion perpendicular to the direction of propagation, and this is the mathematical equation which shows the S waves. Okay, so this is the kind of a diagram which I have taken from this website. As you can see, the compression and the dilation, and this is the undisturbed rock. So a P wave, we can say, is a sound wave traveling through a rock. It's a kind of a, you can imagine it to be a sound wave. So in a P wave, the rock particles are alternately squished. They're squished together and pulled apart, which is called compression and dilatations. Also, they are called compressional waves. So what happens is that when it passes through the rocks, it squishes as well as it pulls apart. And this is basically the longitudinal wave which you see, an S wave. The rock particles slide past one another, undergoing a shear stress, something like that. So here is a nice diagram. You can actually make a shear wave by just taking a rope or a spring to a tree, and then you can just shake it free and move it up and side to side. So it's a kind of a simple experiment which you can do at home to create, I would say, S wave or longitudinal wave. So if you want to know more about this P waves and S waves, I'm putting this in the description also. You can check it out. This is a nice website which explains a lot. Okay, so this is a kind of a nice animation. As you can see, this is the P waves. Now you can see it is moving in this way, transverse. And this is the longitudinal wave, so it is just moving. So on the S waves, now if you can imagine, there are certain rocks, how they will move compared to that of the P waves. So here is a seismometer, and scientists use seismometers to make measurement of seismic waves. Seismometers actually measure the vibration of the ground relative to the instrument, and data from seismometer, also called seismogram, it shows the movement along the x and y axis. Here is a nice schematic diagram, and here you can see what happens is that this waves actually, you can see that the green one is the S wave, which is actually I would say first denoted in seismometers, and then comes this one, the P wave, which is written in red. So it's a kind of nice diagram to make you understand. So the speed at which seismic waves actually travel depends obviously on the properties of which the material it is traveling through. So denser material is a faster seismic wave. So here is a nice diagram which I have taken from earth.stanford.edu. And here you can see that if I take the densest, that is 2.7 to 3.1, which is basalt, here you can see P wave's velocity compared to others is the highest. And similarly S wave compared to that is the highest. Wherever if I take a little bit lesser denser medium, which is dry sand, you can see it reduces to 400 to 1200, and it also reduces to 100 to 500. So this is quite clear, isn't it, from this kind of a chart, that if you see the density compared to P wave and S wave, the denser is the medium, the speed is higher. The lesser denser, the speed is lower. We come to a very important understanding which we started learning in the first video, that is, what is a frequency and an angular frequency. Now you see, frequency and angular frequency simply is actually denoted by this equation. So we can see directly that angular frequency has a dimension of angle over time, and S frequency, F, tells the number of cycles per second, which is denoted by this omega sign. Now, if I take a basic definition, what is a frequency? I would say it's a measure of how many complete cycles of a periodic waveform, for example, a sine wave, occur in a second. So it is measuring the how many cycles. That means in 1 second, and it is measured in a hertz. And this is the relation, frequency equal to 1 upon t, and this t is actually the time period, which is the time it takes to complete one full cycle of the wave. So unit is hertz per second, and relation to period is obviously inversely related. As frequency increases, the period decreases. So if a wave completes 10 cycles in 2 seconds, what would be the frequency? It will be just this, it will be 5 hertz. Now, angular frequency, which is denoted by the Greek letter omega, is measured of the rate of change of the phase of a wave with respect to time. It is basically describing an oscillatory motion in terms of radians per second. So it is, if I talk of mathematics, it is represented by omega and is related to frequency as this. So omega will be 2 pi f, where we are defining this in terms of radians. So further, in angular frequency, we can say that it is radians per second. Angular frequency actually is directly related to the frequency. Angular frequency, I would say, is a way of describing oscillatory motion in terms of angles covers per second. So if I take a frequency of 5 Hz, its angular frequency will be 10 pi rads per second. So we can summarize this in this way, that frequency represents just the numbers of cycles of waves and is measured in hertz, and angular frequency is the rate of change of phase in terms of radians per second. That means the relationship is omega equals to 2 pi f. So this is the cycles waves per second at the rate of change of phase in terms of radians. Now this is very important. I think that this actually creates a lot of confusion among young students who are learning wave mechanics, is that how can you actually distinguish between a frequency and an angular frequency? The things are pretty simple. Simple is that angular frequency is the rate at which an angle is changing. Whatever, I mean to say, angular frequency, angular velocity. So it is actually found in part of the trigonometric function or in complex exponential, and it is radians per time. Regular frequency is something different. It is actually number of events per time. This is the angle at the rate of which it is changing, and this is number of events per time. And in either case, the terminology is not essential, as knowing of what you are denoting as f or omega really means in the system you're looking at it. Also remember this one. This one is very easy to understand. Regular frequency is rotations per second. Angular frequency is radians per second. So rotation means a complete rotation, which is obviously will be 2 pi radians. To explain things further, here are a few quick points. Frequency and angular frequency do not have the same units. Obviously, the angular speed, the rate of change as in circular motion, the frequency is 1 upon t, or the number of periodic oscillation it takes, and angular speed or angular frequency relates to, always mention that angle means it relates obviously to angles. So how much angle is covered in a certain period of time. So these are some of the distinguishing features which, when comes in your mathematics and further study, you can distinguish between what is a frequency and an angular frequency. So right now it is a quick time that we should summarize what we have learned today. So we have learned the relationship between wavelength, frequency and speed. Lower frequency, higher frequency, how it is related to the electromagnetic spectrum. We learned a good amount about P waves and S waves and how they are responsible for earthquakes, frequency and angular frequency, and how we can distinguish, understand, and what is the real relationship between frequency and angular frequency. So what we will do is that in the next part of the video, we are going ahead, we will cover some part of the basis vectors operation, some of the basic vectors. I will just quickly skip over this, complex numbers and imaginary numbers, Euler relations, and then we will go into the real part of wave mechanics, which is the wave function. So that's all for today's video. I would like to thank you immensely for taking up the time to watch this video. If you like the video, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. This is my Gmail ID which you can contact. This is my other channel on General Theory of Relativity, and you can follow me further on my Facebook, LinkedIn, Instagram and Twitter account. So I will be continuing with this video series on wave mechanics, because there is a lot of things to learn, a lot of things to go, and a lot of things to explore in the coming few episodes of wave mechanics. So if you really like the video, put on the comments and let me know how this series is going, and Physics for Students will be back with few more and more videos. Till then, have a good day and goodbye.